Okay, class, let's move on to stage 2 of carbohydrate metabolism. In the previous video, we went through the introduction and we went through all the stage 1 reactions. So our stage 2 reactions begin with converting, and if you can hear the rumbling of the construction behind me, I'm sorry. Stage 2 reactions begin by interconversion of GAP, or glyceraldehyde 3-phosphate, and DAP, which is dihydroxyacetone phosphate. Okay? And I'm not going to redraw those structures because there's no real reason to. Um, you have them in your notes from the last video. Okay. This reaction is catalyzed by triose phosphate isomerase. Okay. Um, the reason that this needs to be done is that glyceraldehyde 3-phosphate is the substrate for reaction 6. Okay? And so we need to have that dihydroxyacetone phosphate converted to GAP. But this is a reversible process. Okay? And so that means that the delta G for this process is on the order of 0. Okay? As with any of these processes that are reversible or operate by equilibrium, purely by equilibrium. Okay, most of the reactions, unless we've drawn them out as irreversible, have a delta G on the order of 0, and that helps conserve some of the efficiency of the process. Okay, so then we move to reaction 6, all right, and that is the oxidation of glyceraldehyde 3-phosphate. Okay, and again, I'm not going to draw out glyceraldehyde 3-phosphate again, so I'm just going to abbreviate it as GAP. Okay, and okay, computer, thank you for that. I appreciate that. GAP is combined with NAD, not NAP. Sorry, I'm reading ahead in my notes. NAD, and that's NAD plus inorganic phosphate. Okay, and this equilibrium is driven by GAP dehydrogenase, which you will see abbreviated often as GAP-DH. Okay? And the product we get out of this is very similar to what we started to do with what we started out with when we were starting to convert glucose. Okay, we get a bisphosphate. Only this bisphosphate has a carbonyl. Okay, and so this is glycerate. One three. bisphosphate. Okay, and I didn't address this in the previous video, but um, I know that in organic you're taught to call things as di for two. Okay, um, we also know that bi means two, bis as well means two. Okay, so these three terms are equivalent. You'll see them used interchangeably. I'm not entirely sure where the roots of each of these prefixes comes from. Um, I imagine that that has something to do, like the origin of the name has something to do with the usage of the particular prefix. Um, I can't give you any more information. If you want to look it up on your own, share it with the class via the comments or something else, that'd be great. Share it with me. I'd love to know. I'm curious. All right. Okay. So now we will move on to reaction 7. Okay. And so the first thing we have to do is we now have to transfer a phosphoryl group. All right. So we have a phosphoryl group transfer. Right. So we start with our we start with the right structure. That's what we start with. You didn't catch me on it. Come on. Just kidding. Just kidding. So we start with the glycerate 1,3-bisphosphate. Okay, and again, I'm using the condensed phosphates for this. We add to it a mole of ADP. Okay, and then this equilibrium is controlled by phosphoglycerate kinase. And remember that a kinase involves the movement of phosphate groups, right? And so what we get out of this is we get the resulting deprotonated acid. Okay. And so now we have just glycerate 3-phosphate. All right. Give me one moment so I can close this window so that the construction sounds stop. I think the apartment complex next door is having some renovation work done, which one could argue now is not the time, right? After this, we have to interconvert. Okay. We have to interconvert glycerate 3-phosphate and glycerate 2-phosphate. Okay, so we need to move the phosphate group. All right. So we have glycerate 3-phosphate with its free hydroxyl. And it with the addition of an inorganic phosphate group undergoes an equilibrium where we have a transition state. Okay? And that transition state is a glycerate 2,3 bisphosphate. Okay? And then in the next equilibrium step, we lose an inorganic phosphate by addition of water to get glycerate 2 phosphate. I want you to think about this. Why would this occur? Why would this occur? Well, because hydroxide, right? Think back to organic chemistry. Hydroxide is not as good of a leaving group as phosphate, right? So both of these reactions, both equilibria, are catalyzed by phosphoglycerate mutase. Okay, phosphoglycerate mutase. And both equilibria require magnesium. Okay. Now, there's another the next step here involves converting this, okay, into the equivalent of what would be an enol. All right. So let's go over that real quick. If you remember from organic chemistry, an enol is a molecule that has a double bond adjacent to a hydroxyl group. And these can undergo a tautomerization reaction, okay, between this and an equivalent carbonyl form. Okay. Right? With the hydrogen being transferred. Okay. So it can undergo a tautomerization back and forth between these two forms. By putting a phosphate group instead of a hydroxyl group here, right? By having phosphate, that blocks this tautomerization from occurring. We don't get that product. Okay, so it locks us, it allows us to create an enol-like structure without risking it converting to a different product. Okay, so it's really ingenious in that way. Okay, because the next reaction is the dehydration of glycerate 2 phosphate all right, 2, and this name is long, so don't panic. Phospho enol pyruvate. Okay? Side note, now that you know a whole bunch of the reactants or reactions that take place, right, in carbohydrate metabolism, if you want to scare somebody half to death who's really big on that clean eating movement, right, all you have to do is tell them, oh yeah, my cells are full of phosphoenol pyruvate. It's a totally natural process, but they'll freak out because they can't pronounce the word and they don't know what it means. And then they'll tell you something like you're going to get cancer. Okay? All right. So, goofy aside over. No, Dr. C. Don't get rid of a carbon that's supposed to be a carbon. There we go. So this conversion, this enol formation, is catalyzed by the enolase enzyme. At least we have one enzyme whose name is easy to remember, right? And so we get this phosphate, this phosphoenol. Okay? All right. And this is abbreviated as PEP, right? So now you know, well, actually, putting some PEP in your step has nothing to do with this. Probably. Possibly. It's a good question. I'm glad you asked. I'm glad you asked, Kalani. You know, because you would be the one who would ask if that has something to do with putting PEP in your step. That's a good question. To which I say, do some research, see what you can find. Okay. This happens by an E1 pathway. Okay. So, am I going to draw out that E1 pathway for you? That's right, Myra. No. No, I'm not. Okay. I expect you to be able to do it on your own. Try it out. Okay. All right. But again, notice that we have this phosphate group here, so this can't be tautomerized. Okay, this can't tautomerize. It's locked in this form. Our bodies are more intelligent than we give them credit for. Right? 10th reaction is the synthesis of pyruvate. Right? So we're going to convert PEP to pyruvate. Okay? So we have our PEP. Right? There's our PEP. And we need a phosphate acceptor. That would be our friend ADP. In the presence of magnesium ions. Okay? We can kick out ATP. Right? And then we're left with enol pyruvate. Now, I think you all can see there is something that can happen, especially in the presence of acidic protons, right? And that is that can be converted very quickly to keto pyruvate. This is enol pyruvate. I don't know why I put a cross through that. This is keto pyruvate. Okay. This is the more stable form. Okay. And I apparently did not write down the enzyme in charge of this reaction, so you know what I'm going to say. Research. Look it up. Okay. So now we have some further notes. Okay. Once we have our pyruvate, we can break it down further. All right. This would give us more ATP. All right. But it depends on two things. First is, of course, the cell type that the metabolism is taking place in. Okay. Second is the presence of oxygen. All right. Because if oxygen is not readily available, that very much changes things. Okay. So if oxygen is available, right, that means we're under aerobic conditions. Okay. And so what this means for our pyruvate is that pyruvate is converted to acetyl coenzyme A, which you will see abbreviated as acetyl-CoA. All right. And then enters the citric acid cycle. Right. So when we are exercising, this is how this most of the time for our bodies, this is how our metabolism takes place. Okay. We break it down into this pyruvate, and then our pyruvate is converted to acetyl-CoA, and then acetyl-CoA goes into the citric acid cycle to give us full ATP, and that ends with CO2 and water. Okay? It's as though we completely combust the glucose. All right? The other option, okay, is if oxygen is not available, if it's scarce. Okay? This blocks further oxidation of the pyruvate. Okay. And so as a result, cells are forced to reduce the pyruvate. Okay. All right. And they use that to regenerate the NAD plus to enhance metabolism, right? Because NAD plus is a key reactant in one of our previous reactions, right? We call this process fermentation. Okay. And if I ask you right now, what are some products of fermentation? I bet one of the first things that you might think of is ethanol, right? Ethanol. Because it is the primary fermentation product of yeast. And then if that is left exposed, right, to air, we get ethanoic acid or acetic acid. Right? Also known as vinegar, right? Just so happens to be my favorite acid. Might be a bonus point on your next exam. Who knows? Okay. So that is a fermentation pathway. That is caused by anaerobic respiration of the yeast, right? Anaerobic metabolism of the yeast. All right. Uh, Other notable fermentation processes, right? I'm going to make this note in the upper right corner here. Okay. Other notable ones, acetobacters, right? Those would be the bacteria that are found naturally to make wine. Okay, those produce acetic acid as their metabolism byproduct. Okay, they're not like yeast; they don't produce ethanol, which is then converted to acetic acid. They convert directly to acetic acid. Okay, um, lactobacilli, the lactobacillus family, right? They create lactic acid as part of their anaerobic or their anaerobic metabolism byproducts. Okay, um, that you'll find in everything from kosher pickles to yogurt. Okay, and then there are the bacteria C. aceto, and you'll have to forgive me. This one is in Latin, and I don't really know how to pronounce it. Butyllicium. I'm sorry to all the biologists who might watch this. I'm sure I just butchered that pronunciation. Okay? But these bacteria produce butanol as their fermentation byproduct. And this used to be our primary way of getting butanol. Okay? For our this was how, back in the day, Sigma or VWR would produce butanol. Is they would allow these bacteria to anaerobically metabolize glucose to butanol. Okay. Since then, petroleum-based processes have replaced that, so we can actually convert, petroleum byproducts to butanol, and then use it from there. So, which is much more efficient, both energetically and chemically. Okay. All right. Let me check the time real quick. And that about covers us. So, next video, we will go over some of the energetics of glycolysis and some of the things about glycolysis regulation, various enzymes involved in that process. And then we will start talking about glucogenesis and eventually move into nucleic acids. All right? So if you have any questions, remember, email me. You all know my office hours. I finally figured out Zoom, so, we can do face-to-face meetings. It's not a problem. Uh, Text, call, whatever you want to do. All right? See you then.